Continuing our discussion of Chapter 3 of Part 1 of Individuation in the light of notions of form and information. Over the last couple readings, we've been looking at Simondon's interpretation of quantum physics and the transformation of the notion of the individual that it brings about. So we saw, I think, at the beginning of last week or the week before, we saw his discussion of the way that the relativistic physics changes the notion of the individual, because the particles in a relativistic physics have the capacity to increase their mass or energy indefinitely as they approach the speed of light, and so this indefiniteness or this capacity to increase or change the essential qualities of particles contradicts the substantialist or atomistic account of what these particles are, according to which the particles themselves would not have qualities, because qualities are explained by the combination of different particles in various ways. The particles themselves in a substantialist or atomistic theory are supposed to stay the same, and then they just come into various combinations, and those combinations are what give rise to the various qualities that we can observe in composite bodies. But the fact that the seemingly essential qualities like mass and energy of a particle can increase beyond any given limit under relativistic physics shows that these seemingly essential qualities are not fixed in the way that they would be in a substantialist theory, so that we can't treat the particles in a relativistic physics as if they were little miniature substances in the way that we could in the pre-relativistic physics. And he points also to the role of interaction. So the way that the interaction of particles in a relativistic physics can, by changing the velocity of a particle, will also change its mass, because of the way that the mass increases as a particle approaches the speed of light. So again, the seemingly inherent properties of the particle can change as a result of interaction with other particles, which again is in contradiction with the substantialistic account of how particles are supposed to work. And so then we passed to the change in the notion of the individual that comes about through quantum physics. So this is important because, so for Simondon, we've seen on a number of occasions he wants to come to a conception or develop a conception under which relation would have the status of being, so that what relation in the proper sense, or in the sense that he wants to use that term, is not something that's external to the being of the terms that are related to each other, but it's something that makes up that being, and it's a part of that being. And so he's argued in earlier parts of the work that in order to have that kind of relation, that ontologically strong sense of relation, there has to be a discontinuous term and a continuous term. So the relation has to be asymmetrical in that sense. So that discontinuity is what is characteristic of quantum physics, in the sense that we have discontinuous energy states of particles, so that they can only exist at integer multiples of a particular constant, Planck's constant. So there's no energy state that a particle can occupy that is, say, 1.5 times that constant. It's always going to be either at 1 or 2 or 3, etc. Times that constant. So there's a sort of jump from one energy state to the next one without passing through the intermediate energy states. And that's the discontinuity that characterizes quantum physics, as opposed to the continuous physics of the pre-quantum world. And then we also saw briefly, Simondon pointed to the specific interpretation of quantum physics that he's working with, which is Louis de Bruy's double solution theory. And so we saw he explained a little bit the history of this account. So de Bruy came up with the double solution theory, and so according to this theory, the wave function has two solutions. So it has the one linear solution, which is the one that's been retained by standard interpretations of quantum physics, and that has a probabilistic meaning. But then there's also a nonlinear solution to the wave function, which has a real physical meaning, is not probabilistic. And so de Bruy came up with this idea, but then the mathematical difficulties of working with this nonlinear solution led him to propose a simplified version of the theory called the pilot wave theory, under which there would be a particle, and then the wave function would be a real wave that guides the particle. So that's where the term pilot wave comes from. And so the wave particle duality or complementarity would actually be a real physical duality, not just some sort of conceptual duality. So that there really is a particle and a wave that interact with each other. And so de Bruy presented this the pilot wave version at the Solvay conference in 1927. And then he got some objections as to the adequacy of this theory that he apparently did not answer very well. And everyone was convinced that the theory was sort of hopeless, including de Bruy. He gave up on the theory and adopted the standard interpretation of quantum physics. And it was only in the 1950s that David Bohm rediscovered the pilot wave theory and countered the objections which had suggested that it was not possible to develop a theory of that kind, a so-called hidden variables theory. So David Bohm developed sort of set out the theory, and he resolved some of the mathematical difficulties that had led de Bruy to adopt the simplified version. And so after that, after Bohm proposed or sort of reestablished the theory, de Bruy went back to his double solution version, and he worked on that. And he also proposed that this was a way or sort of gave a promising lead for how to unite quantum physics with relativistic physics, which is still an open problem today. And so that's sort of what we've seen in the last couple of weeks. That's like a little recap. But sorry, that was a little bit long. So let's start our reading for today. We're at the top of 143. I'll read the first page or so. The Compton effect, which is produced with X-rays and gamma rays, consists in a diffusion of radiation by matter. But in the Compton effect, the changes of frequency that correspond to this diffusion do not depend on the nature of the diffusing body and only depend on the direction in which the diffusion is observed. This effect is interpreted by saying that the X-ray and gamma photons encounter in the diffusing body the free or approximately free electrons that are at rest or almost at rest. The variation of the photon's wavelengths is due to an energy exchange with an electron. The trajectories of the photon and of the electron can be slowed down after this energy exchange, which is a veritable shock by means of the Wilson chamber, when the photon still produces, after having struck the electron, the birth of a photoelectron, since it has encountered a gas molecule. The electron's trajectory is directly visible in the Wilson chamber due to the ionization that it produces. This is Compton's and Smith's experiment, and Simon's experiment. To clarify this relation of the wave in the corpuscle, Louis de Bruy has resorted to a critique of the concept of corpuscles such as it is used by physicists, and he opposes two conceptions of the corpuscle. The first is one that conceives the corpuscle as a small, well-localized object that depicts in space through time a sensibly linear trajectory, upon which at each moment it occupies a well-defined position and is animated by a well-determined speed. But there is a second conception according to which it can be said that a corpuscle is a physical unit characterized by certain constants, mass, charge, etc., and capable of producing localized effects in which it intervenes totally and never just in part, like, for example, the photon in the Compton Effect or the photoelectric effect. Yet, according to Louis de Bruy, the second definition is a consequence of the first, but the inverse is not true. One can indeed imagine that there are physical units capable of producing local effects, but which cannot be constantly identified with small objects depicting linear trajectories in space. However, we must choose between the ways of defining the relation of the wave and the corpuscle based on this moment. Which term is more real? Are they just as real as each other? Is the wave merely a sort of field of probability, which is, for the corpuscle, the probability of locally manifesting its presence by an observable action in such or such point? Louis de Bruy shows that three interpretations are logically possible. The author has wanted to accept what would allow for the broadest synthesis of the notion of waves and corpuscles, starting, as we have tried to indicate, from the two cases where the necessity of this bond was apparent, that of the photon and that of the quantified movements of corpuscles. He has wanted to make this bond possible for electrons and other elements of matter or of light by linking, through formulas wherein the Planck constant h would necessarily figure, the aspects of the wave and the corpuscle indissolubly tied one to another. And so Angus has posted a question in the chat here about what I mentioned earlier on uniting relativity and quantum physics. So the question is the idea that uniting relativity and quantum physics would result in a concept of light that is both continuous and discontinuous, and therefore capable of explaining individuation. I'm not 100% sure that's whether or not that's what Simondon has in mind in his discussion of the double solution theory. Because earlier in the text, he had suggested that the photon concept is not something we should regard as having reality. So he pointed out that the photon concept is introduced in physics to explain the photoelectric effect, by which a piece of metal emits the electrons when it's irradiated with light at a certain frequency. And then he points out that this photon concept is useful in this one area of physics, in this one range of frequencies, but in other ranges of frequencies, it's not useful. And he argues that if we wanted to grant reality to the photon concept, then it should be it should make itself known or make itself felt in the whole range of electromagnetic radiation, and not just in one particular domain or one subset of that range. So I think he doesn't want to grant something like individuality or individuation to the photon. But I think in the case of other particles like electrons and so on, that same wave-particle duality exists, and it will be understood as something like the relation between a continuous and a discontinuous term that is characteristic of individuation for Simondon. And so I think in the case of other particles that Simondon does regard as real, I think he will grant that this double solution theory allows us to understand their individuation in a way that the other theories don't. So in the bit that we just read, he's setting up the three possible interpretations of the relationship between the two notions of a particle. So the one notion is of a particle as a small, well-localized object that has a determinate trajectory through space over time, and a determinate speed at every moment. And And then the second notion of a particle is one that is more abstract. So it's just a physical unit characterized by certain constants of mass, charge, etc., and capable of producing localized effects in which it intervenes totally and never just in part. So it's that discreteness or discrete character of the particle. So like in the photoelectric effect, when light is considered as having this particulate structure or this particle nature, it's because the photon instantaneously, the energy of the photon is absorbed instantaneously, and when the frequency is above the threshold, then the metal emits the electron. It doesn't have to sort of store up energy over an interval of time. It instantaneously reacts. So the photon has this all or nothing effect. And so this is what characterizes the more abstract notion of the particle. It's something that has an effect at a location instantaneously or as one unit, and not as something that can react in part or have a partial action. And so we're going to see the three possible interpretations of the relationship between these two notions of a particle, because the second one, the more abstract one, implies the first one, or sorry, the other way around. The more particular one implies the more abstract one, but not the other way around. So we can have various ways of interpreting the relationship between them, and that's what we'll see in the next bit. So if someone else would like to read, we can go on to those interpretations.
The first type of relation between waves and corpuscles comes from the work of Arthur Schrödinger, which consists in denying the reality of the corpuscle. Only waves would have a physical signification analogous to those of the waves of classical theories. In certain cases, the propagation of waves would give rise to corpuscular appearances, but these would be nothing but appearances. Quote, at the start, to clarify this idea, Mr. Schrödinger wanted to assimilate the corpuscle to a small packet of waves. But this interpretation could not be sustained, given the fact that a packet of waves always has a tendency to rapidly and incessantly stretch out in space, and would soon not be representing a corpuscle endowed with a prolonged stability. Louis de Bruy does not accept this negation of the corpuscle's reality. He declares that he wants to accept the wave-corpuscle duality, quote, as a physical fact. The second interpretation concedes the reality of the wave-corpuscle duality and wants to give it a concrete signification conforming to the traditional ideas of physics. And it considers the corpuscle as a singularity within a wave phenomenon of which it would be the center. But Louis de Bruy says the difficulty is knowing why wave mechanics successfully utilizes continuous waves without singularities of the type found in the continuous waves of the classical theory of light. Lastly, the third interpretation consists in only considering the ideas of the corpuscle and of the continuous wave, and in regarding them as complementary facets of reality, in the sense that Bohr gives this expression. This interpretation is qualified by Louis de Bruy as quote-unquote orthodox. The second interpretation was at first that of Louis de Bruy in 1924, following the defense of his thesis. He considered the corpuscle as a singularity within an extended wave phenomenon, the whole of which forms nothing but a single physical reality. Quote, since the movement of the singularity is tied to the evolution of the wave phenomenon and forms its center, it would depend on all the circumstances that this wave phenomenon would encounter in its propagation in space. This is why the corpuscle's movement would not follow the laws of classical mechanics, which is a purely punctual mechanics, in which the corpuscle is merely subject to the actions of the forces exerted upon it along its trajectory, without undergoing any repercussion from the existence of the obstacles that can be found farther along its trajectory. In my conception, on the contrary, the movement of the singularity would be subject to the influence of all the obstacles that would influence the propagation of the wave phenomenon with which it is interdependent, thus explaining the existence of interferences and diffraction, unquote.
Right, so we have these three interpretations that all have this seemingly fatal flaw or this decisive objection against them. So the first one is one that denies any physical reality to the corpuscle aspect or the corpuscle part of reality. So it says that the wave is the only real physical, the only physical reality is the wave, and then the particle, which or what is regarded as a particle, would in fact be a packet of waves. So a particularly dense region of the waves or something like that. And so the objection to this account is that it doesn't account for the stability of the particle, so that the packet of waves will sort of dissipate over time. It will no longer have that packet characteristic or that form that approximates a particle. And so we can't explain on this account how particles have something like stability or a tendency to maintain that particle character over time. And then the second interpretation grants the wave corpuscle duality a real physical existence, a real physical nature. But it regards the corpuscle as not just a packet of waves, but as a singularity in the wave. So it's a singular region within the wave function, and so the wave and the particle would both be physical realities, but they're related to each other by this notion that the particle is a singularity in the wave function. And this is the theory that Bruy had adopted in the 1920s. But the objection to this theory is that in the treatment of light and in wave mechanics in general, there's no sort of intrinsic reason to think that there are these singularities. So wave mechanics is capable of working with continuous waves, and the singularities don't really come up, or there's no reason to think that there would be this singularity. So it has this interpretation has a sort of artificial character because it's a sort of post hoc suggestion that there should be these singularities, but the singularities themselves don't appear anywhere else. So that's the second objection, or I guess you could put it in other terms, that so if the wave phenomenon really is or really does have singularities in its real physical manifestation, then why is it that wave mechanics is capable of operating successfully with a continuous wave without singularities? So that's the problem or objection to the second theory. And then the third interpretation is the standard interpretation, part of the Copenhagen interpretation of quantum physics, which regards the wave and particle as being two complementary descriptions of reality, so that they're in some sense relative to our knowledge. So we have to describe reality in terms of both wave and corpuscle, but we don't have any sort of capacity to ascribe physical reality to either of those two aspects on their own. And so this is the standard interpretation, which has a sort of epistemological limitation built into it, so that we can only talk about how we describe reality using these concepts, but we can't really talk about what reality is like, physical reality is like itself. So that's the third interpretation, and so he doesn't set out what the real objection to that third interpretation is, but I think it's precisely that epistemological limitation is what Simondon finds objectionable, and or following de Bruy, what de Bruy finds objectionable is that epistemological limitation, the fact that on this interpretation we can't actually talk about what physical reality is like. We can only talk about our descriptions of physical reality. And so some way out of some alternative interpretation has to be offered to explain how we or what physical reality is like if quantum physics is a correct description of reality. What does that tell us about what physical reality itself is like? So that's what we're aiming towards here. Maybe one other point before we go on is in that last paragraph at the bottom of 144 and top of 145, in that quote from de Bruy, he explains what is new or what is different about this second interpretation that considers the corpuscle as a singularity within a wave phenomenon. So under this account, we have a natural or a plausible explanation for why these particles should behave in a way that that doesn't follow the laws of classical mechanics. So that, for example, the existence of interference in the two-slit experiment, which on the standard interpretation, on the Copenhagen interpretation, is interpreted to mean that there's no fact of the matter about which slit the particle passes through. It's not a determinate fact, and it's only when we measure it, the location of the particle when it strikes the photoelectric plate at the end of the experiment, or when it strikes whatever measuring apparatus is at the other side of the two slits. It's only when it's measured by that apparatus that the particle has a determinate location. And so under de Bruy's interpretation, the particle does have a determinate location and it does pass through one slit rather than the other. But the waves that, or the wave phenomenon that guides the particle, or that determines the particle's trajectory, interacts with the apparatus, the two slits, and it's that wave aspect, that physical wave, that produces the interference effect on the back wall of the apparatus, so that we have a physical explanation for the sort of strange behavior of particles at the quantum level, rather than just suggesting that there's some kind of epistemological limitation to what we can know about the particles. So that's what's new about de Bruy's interpretation. Okay, so we can go on to the next bit if someone else would like to read.
However, as Louis de Bruy says, wave mechanics has developed by only contemplating continuous solutions without singularities for equations of propagation. These solutions are customarily designated by the Greek letter psi. If the propagation of a wave, a flat and monochromatic psi wave, is associated with a uniform and rectilinear movement, then a difficulty is presented. The phase of the wave that allows us to define the frequency and wavelength associated with the corpuscle indeed seems to have a direct physical sense, whereas the wave's constant amplitude seems to be just a statistical representation of the possible positions of the corpuscle. As Louis de Bruy affirms in the same annual conference presentation, quote, "Thus there would be a mixture of the individual and of the statistical that would be mysterious and would seem to have to be clarified." This is why de Bruy will postulate in a May article of Journal de Physique that all continuous solutions for the equations of wave mechanics are somewhat doubled by a solution with a singularity u that carries a singularity that is mobile in general, the corpuscle, and has the same phase as the solution psi. Between the solution u and the solution psi, which both have a wave form, there is no phase difference, since the phase is the same function of x, y, z, t. Yet there is a considerable difference of amplitude because solution u conveys a singularity, whereas that of psi is continuous. If the equation of propagation is supposedly the same for u and for psi, then a fundamental theorem can be demonstrated. The mobile singularity of u must eventually describe a trajectory such that in each point the speed is proportionate to the phase gradient. Quote, "It could be said that this is how the reaction of the propagation of the wave phenomenon on the singularity that forms its center would be translated. I am also demonstrating that this reaction could be expressed by considering the corpuscle singularity as being subject to a quantum potential that was precisely the mathematical expression of the reaction of the wave on it," unquote. Thus, the diffraction of light by the edge of a screen can be interpreted by saying that the corpuscle of light is subject to an action of the screen's edge and is thereby diverted from its rectilinear route, just the partisans of the old corpuscular theory of light proclaim, but by considering the action of the screen's edge on the corpuscle takes place through the intermediary of this quote-unquote quantum potential, which is the mathematical expression of the wave on the corpuscle. The wave would therefore serve as a means of energy exchange between the corpuscle and the screen's edge. In this interpretation, the U wave with its mobile singularity therefore simultaneously constitutes the corpuscle and the wave phenomenon that surrounds it, which is a single physical reality. What describes physical reality is the U wave and not the psi wave, which has no real physical signification, since the psi wave is deemed to have the same phase as the U wave, and the corpuscle singularity is always displaced by following the phase gradient. The possible trajectories of the corpuscle would coincide with the curves orthogonal to the surface equal to the phase of psi. This would lead to considering the probability of finding the corpuscle in a point as equal to the square of the amplitude or intensity of the psi wave. This principle was already accepted for quite a while in wave mechanics, since it was necessary for establishing the theory of the diffraction of electrons. In 1905, Einstein had already shown that the probability for a photon to be present in a point of space is proportionate to the square of the amplitude of the light wave associated with it. Here we rediscover one of the essential principles of the wave theory of light. The density of radiant energy is given by the square of the amplitude of the luminous wave. In this case, the psi wave seems like a purely fictive wave, a simple representation of probabilities. But it is worth mentioning that this formal and somewhat nominal characteristic of the psi wave was only just so because in phase concordance with it, there was a U wave phase with a singularity that really described the central corpuscle of an extended wave phenomenon. And this was how Louis de Bruy concludes his retrospective exposition in 1953. Quote, if we could have the impression that the psi wave fully sufficed to describe the behavior of the corpuscle such that we could observe it experimentally, this would be due to the coincidence of phases that formed the cornerstone of my theory.
Yeah, so this is the sort of key notion of the double solution theory. So that's why it's called double solution, is because we have these two different solutions to the wave function. So the one, the psi wave or the psi solution is a purely probabilistic a purely probabilistic description of the probability for a particle to be located at a certain location. And under the standard interpretation of quantum physics, that's all there really is to know, is that probability. So there's this inherent indeterminism about reality, so that it's actually there's no fact of the matter about where the particle is determinately until it's measured, and it's only and before measurement, all we have is this probability of location of a particle in a certain location, and so that's the psi wave or the psi solution to the equations of propagation. And so the psi wave has this continuous character. It doesn't have singularities. And then de Bruy proposes that there's also this U wave, and the U wave would have a singularity within it, which is what accounts for the particle, or the appearance of a particle. And the U wave would, in fact, be a physical wave. It's not probabilistic like the psi wave. And so some of the strange phenomena like diffraction and interference would be accounted for by the way that the wave interacts with the obstacles or the arrangement of the environment. And so there is a real exchange of energy between the particle and the edge of the screen in the diffraction experiment, so that the particle is diverted from the straight line path, and so this version, this U wave, has an extra term compared to the standard theory, which is precisely the quantum potential that he talks about. So it's a more complicated mathematical expression than under the standard interpretation. By being more complicated, or by having this extra term, it gives a physical meaning to the solution of the wave function, rather than a purely probabilistic one. Right, and Angus posted a question in the chat about so asking, the psi wave solution holds that the particle in itself has a probabilistic position. So maybe to sort of clarify, so the psi wave is in itself is just a mathematical solution of the equations for the wave function. So it doesn't in itself say anything about what the physical character of that solution is. But under the standard interpretation, the Copenhagen interpretation of quantum physics, that probabilistic depiction of reality is the only fact of the matter about the the particle until it's measured. So there's no determinate location of the particle until it's measured, and then in that pre-measurement state, it only has a probability of being located at various positions that's determined by that function. So the sort of major problem with that account is that there's no good explanation of what it means for something to be measured in physical terms. So that, of course, in real life, we know perfectly well what measuring means. We have instruments that can measure whether a photon strikes a piece of film or an electric sensor or whatever. But there's no explanation in terms of, under quantum physics, you have this sort of probabilistic reality, or we have this behavior of the particles determined by this psi wave, but then measurement is supposed to collapse that wave function down to one possibility. So what exactly that means, whether there's a physical process of collapse of the wave function, or whether this is a purely epistemic transformation, that's something that is still under debate, and that's what is called the measurement problem within the foundations of quantum physics. So that's the sort of major weakness, or the major open problem in the Copenhagen interpretation of quantum physics. Okay, so I think we can go on. I can read the next page or so of this multi-page paragraph. So I think we just read the quote from de Bruy beginning, "If we could have the impression." I think that's where we ended, right? In order to be received at that time, this theory required that we rework the theory of the phenomena of interference, for example, that of Young's slits, by only utilizing the U wave with its singularities. It would be just as necessary to interpret, with the help of the U wave, the wave mechanics of systems of corpuscles developed in the framework of Schrödinger's configuration space. But in 1953, Louis de Bruy proposes a modification of the U wave. In 1927, I considered it as a solution with a singularity of the linear equations accepted by wave mechanics for the psi wave. Various considerations, particularly the assimilation with the theory of generalized relativity, of which I will speak later, have made me think that the veritable equation of U wave propagation could be nonlinear, like the ones we encounter in Einstein's theory of gravitation, which is a nonlinear equation that would admit as an approximate form the equation of wave mechanics when the values of U would be weak. If this point of view were exact, we could even admit that the U wave does not behave like a mobile singularity in the strict sense of the word singularity, but merely as a very small mobile singular region with dimensions on the order of 10 to the minus 13 centimeters, within which the values of U would be large enough for the linear approximation to no longer be valid, although it would be fully valid in the space outside this very small region. Unfortunately, this change in our point of view does not facilitate the resolution of the mathematical problems that are posed, because if the study of the solutions of linear equations with singularities is often difficult, that of the solutions of nonlinear equations is even more so. Louis de Bruy attempted to simplify his theory for the Solvay conference in 1927 by introducing the notion of the pilot wave, which was essentially the psi wave considered as guiding the corpuscle following the formula speed proportionate to the phase gradient. Since the corpuscle's movement is defined by the phase gradient that belongs to the solutions U and psi, everything seemingly happens as if the corpuscle were guided by the continuous psi wave. The corpuscle would then become an independent reality. This representation was not well received by the Solvay conference, and Louis de Bruy regretted having simplified his theory in the direction of a certain formalism that eventually resulted in a nominalism. The theory of the pilot wave leads to this unacceptable result of determining the movement of the corpuscle by a physical quantity, the continuous psi wave, which has no real physical signification, depends on the state of knowledge of the one who utilizes it, and must vary abruptly when information happens to modify this knowledge. If the conceptions that I have announced in 1927 one day rose again from their embers, this would only occur in the subtle form of the double solution, and not in the truncated and unacceptable form of the pilot wave. Louis de Bruy considers that the first form of this theory, which conveys the U wave and the psi wave, albeit difficult to justify mathematically, is quite superior to that of the pilot wave, since it is capable, in successful cases, of offering an extremely profound view of the constitution of matter and of the duality of waves and corpuscles, and is even perhaps capable of allowing for a rapprochement of quantum conceptions and relativistic conceptions. Nevertheless, this rapprochement is something Louis de Bruy ardently desires, considering it to be grandiose. So there's an explanation here of the distinction between the pilot wave version of the theory and the double solution version. And again, so de Bruy originally came up with the double solution theory, but because of the mathematical difficulties, he simplified the theory and presented it at the Solvay conference in the form of the pilot wave theory. And when that was rejected, he gave up on both forms of the theory. And then David Bohm in the 1950s, 1951, I think, 1952, he rediscovered the pilot wave form, and that led de Bruy to go back to his double solution theory. And so the difference is under the pilot wave version of the theory, the psi wave would govern, so the continuous set of solutions to the wave function would govern the movement of the particle, and so we have a continuous where a continuous function, a continuous wave, which interacts with the particle and governs its trajectory. And so de Bruy's later criticism of this version of the theory is that if the psi wave is probabilistic, then we're using something that has no physical reality, that has to do with our knowledge of the position of a particle. We're using that psi wave as we're attributing to it an interaction with a physical particle. So we have a description of our knowledge is interacting with a physical particle, and what exactly that would mean is something pretty obscure. So that's why he considers the double solution theory to be superior. So under the double solution theory, it's not the psi wave, the continuous solution that has physical reality or that governs the movement of the trajectory, the movement of the particle along its trajectory. It's the U wave with its discontinuity. So the particle is this discontinuous region of the U wave, and so the evolution of the particle, the trajectory that it follows, is governed by a real physical wave and not by a probabilistic wave. So that's the difference between the two versions of the theory. Everyone's pretty quiet today. Not a lot of commentary.
Yeah, that clarification of the difference between the pilot wave and the double solution theory was helpful. I was finding it hard to find anything on the double solution theory itself. It seems like all the kind of basic stuff about de Bruy that I could find on the internet was about the pilot wave specifically. But, as we just saw, he talks about them as different theories, obviously. So it's helpful to get that background and kind of understand the difference between the function of the psi wave and the U wave.
Yeah, I probably about a month ago or a few weeks ago, I knowing this was coming up, I was doing some background research and trying to get a better grasp of the the difference between these two theories, and I ended up having to read most of one of de Bruy's books from 1953, I think, or in the 1950s anyway, where he sets out his double solution theory. But that was pretty much the only source I could find anywhere online was de Bruy's book itself, and I couldn't really find any secondary sources that explained that explained the double solution theory rather than the pilot wave theory.
Is that because the double solution theory maybe isn't like current or something that physicists are talking about these days?
Yeah, it's definitely not something that physicists are like actively researching or something that is prominent. I'm sure there's someone somewhere that is working on it, but I don't know if I don't know if that is sort of a reflection on its value. It could also just as much be a reflection on the difficulty of working with this continuous solution. So the mathematical difficulty it just makes it harder to work with and makes it less rewarding, I guess. It's less likely that you're going to make any progress, whereas other versions, so like the pilot wave version, give you more possibility of progress and being able to contribute positively. So I think that could also be a part of what leads physicists not to work on the double solution theory. But yeah, I'm far from an expert, so it's possible that there are good reasons why the double solution theory is not sort of an active center of research. There could be other reasons that I'm not aware of that lead to that.
I was on and off, so my question is that this part is really challenging to me. So my question is that Simon is trying to interpret the individuation. As far as I understand, individuation is kind of a psychological discipline or area, but he's trying to understand, interpret individuation in terms of so how does it make sense? Like, is there anybody who can help me to understand the relation? And when I talk, should I keep pushing to talk? It's quite inconvenient though.
Yeah, you can switch to voice activated. I think it should be allowed now. I think the settings of the channel should let you do that. But if I understand correctly, you're asking about what the relationship is between the psychological notion of individuation and the physical notion that Simondon is developing. Is that right?
Yeah.
Yeah, that's an interesting question, and it's one that we probably can't fully answer yet because so we're still on the part of the book on physical individuation, and then we have vital individuation that comes next, so the individuation of living beings, and then the next part after that is where we'll get to that answer is the individuation is psychic individuation. It's the individuation of entities with a mind or something like that. And so we'll see that in a bit, but the sort of bigger picture is that he regards vital individuation and psychic individuation as being having this relationship of a sort of slowing relationship, so that vital individuation is a slowing down of physical individuation. So when we saw the crystal example, the crystal individuates instantaneously. So it crystallizes, and then the crystal after the individuation is a sort of dead product. It's just there, and so there's this anteriority. So the already crystallized portion of the crystal is anterior or precedes in time the limit where the crystallization is still occurring. But in the case of a living being, the individuation is ongoing, so that rather than having an anteriority, the whole living being is simultaneous with itself. It exists in one time frame, I guess we could say. And then psychic individuation will again be a sort of slowing down of vital individuation, and another sort of incorporation of the time into a previous level of individuation. So that answer probably won't make a lot of sense yet, but so the short version is that we'll see when we get to part 3 of the book on psychic individuation. We'll get a better understanding of that relationship there.
Thank you. The reason why I asked that was that like Simongdong, like in a way treated like a human being as like machines. Like I mean, the process of like explaining like the whole process, like in terms of physics, quite interesting. And then quantum physics, everything. Actually, at the end of the day, like the physics is associated with the some kind of psychological process, definitely. But this part is quite challenging. And then I have a very thankful for kind explanations. Thank you.
Yeah, this is definitely the most difficult part of the book for anyone who is not already like pretty familiar with quantum physics. I've had to do a lot of digging and secondary reading to try to grasp some of what's going on. So yeah, hopefully the bits that I'm able to share will help to understand some of the physical concepts that he's working with, because he sort of presupposes a lot of knowledge of quantum physics as something that the reader is supposed to have already, which is not always the case. Yeah. Angus pointed out we're not too far away from the vital individuation chapter. We should get to it in the next couple of weeks, and it is much easier. The realm of the living being is a little bit less, or it's a bit more familiar than the realm of quantum physics. So there's less sort of weirdness, and we can have a better grasp of what's going on without having to sort of dig through all these secondary sources.
But at the same time, like thinking about Deleuze's books, and then which also like mentions like a Schrödinger, or makes like a outside think of quantum physics, things like that. Just part quite interesting, and then necessary. I mean, a necessary session.
Yeah, I don't remember where Deleuze talks about Schrödinger.
Not exactly. Sorry, not exactly. While I mean, one Deleuze reading group, when we talked about difference repetition, or some of the things, just like the idea came up, so that's why I just said.
Okay, yeah, but yeah, I can definitely see why some of these ideas might come up again in Deleuze. It makes sense that there would be connections to draw there. Okay, so I think we can go on to the next bit if someone else would like to read, starting from "This is why Louis de Bruy."
This is why Louis de Bruy once again considers the theory of double solution U wave and psi wave, as needing to be studied starting from the moment he witnessed Bohm and Bezier, I hope I pronounced properly, resume this point of view. Following Bohm's attempt, Bezier establishes rapprochement between the double solution and the theorem demonstrated by Einstein. After developing the great lines of generalized relativity, Einstein was preoccupied with the way in which the atomic structure of the matter could be represented by the singularities of the gravitational field. Nevertheless, in generalized relativity, we accept that the movement of the body is represented in a space-time curve by geodesics of this space-time. This postulate allowed Einstein to newly discover the movement of the planets around the Sun and to further interpret by the same token the centennial displacement of Mercury's perihelion. Since then, if we want to define the elementary particles of matter by the existence of singularities in the gravitational field, it would have to be possible to demonstrate solely on the basis of the equations of the gravitational field that the movement of singularities occurs following the geodesics of spacetime without having to introduce this result as an independent postulate. Einstein demonstrated this in 1927 while working in collaboration with Gromner, and then the demonstration was repeated and extended in various ways by Einstein. He collaborated in Fields and Hoffman. The demonstration of Einstein's theory presents, as Louis de Broglie claimed in 1953, a certain analogy with what he had himself presented in 1927 to prove that a corpuscle must always have its speed directed following the phase gradient of the U wave of which it constitutes a singularity. M. Bezier fervently pursued attempt to clarify this analogy by seeking to introduce the functions of the U wave into the definition of the matrix of space-time. Although these attempts to have still not fully ripened, it is certain that the path and his tract is quite interesting, for it could lead to a unification of the ideas of general relativity and wave mechanics. End of quote. Since material corpuscles and photons are considered to be singular regions in the matrix of space-time surrounded by a wave field to which they belong and whose definition would introduce the Planck constant, it would become possible, according to Louis de Broglie, to unify Einstein's conceptions on particles and those of double solution theory. This grandiose synthesis of relativity of quanta would have, among many other advantages, the advantage of avoiding subjectivism, which is related, as Louis de Broglie says, to idealism in the philosophical sense, which tends to deny the independent physical existence of the observer. Nevertheless, the physicist instinctively remains, as Meyerson has strongly emphasized long ago, a realist. End of quote. And he has several good reasons for this. I always confusing. Should I say beginning of quote or which start quote? Quote to start?
Yeah, you can say start quote if you want. It's not.
But I don't have to. But I don't have to. Start quote. Okay. Subjectivity interpretations will always give him a feeling of unease, and I urgently believe that he would be happy to break away from this. End of quote. But this synthesis, which is able to reestablish a much more profound and realistic signification of the double solution theory, would also have another advantage. The singular joints of various corpuscles can in fact encroach upon one another starting at a certain scale. This encroachment is not significant important enough at the atomic scale. Telling you, how can I read this one? 10 to minus 8? Or what should I say? Above?
I think that you can say 10 to the minus 8 or 10 to the negative 8. Yeah, I think either one is fine.
Okay, I can just skip it. To construct the orthodox interpretation, but this does not necessarily apply in the nuclear scale. Could you help me one more time?
10 to the negative 13th centimeters.
Thank you so much. At this scale, it could be that the singular joins of corpuscles encroach on one another, that these corpuscles can no longer be considered isolated. Thus, we see appear a new mode of a calculation of that relation between physical individuation in individuals that would force a consideration of density and of individual characteristics, which are defined as a singularity of the U wave. The theory of nuclear phenomena, and particularly the theory of the forces that maintain the stability of the nucleus, could begin through the new path. Physics could define the structure of particles, which is not possible with the psi wave, that excludes any structure representation of particles due to its statistical characteristic. The new types of mesons that have been discovered could thus be provided with a structure image due to this return to spatial temporal images. The statistical psi wave could then no longer be considered a complete representation of reality, and the indeterminism that accompanies these conceptions, in the same way that impossibility of representing the realities of the atomic scale precisely in the framework of space and time through various variables that would be hidden to us, would have to be considered incompatible with the new representation of a physical reality. Thank you for helping me.
Yeah, that's good. That's a good place to stop because it's a subsection break. So thank you. Yeah, so this long paragraph is about the relationship between this double solution theory and general relativity, and what de Bruy thinks is the analogy between the two is that within general relativity, we have this depiction of matter as a singularity within the gravitational field, so that the mass of a body is represented or is identified with the curvature of space-time. So this is analogous to the representation in the double solution theory of a particle by a singular region of the U wave. And so de Bruy sort of hopes or sets out the ambition of uniting the two theories by something along the lines of representing particles by singularities or singular regions. He suggests that this, and Simondon following de Bruy suggests that this unification would have two major advantages. So the first is that it avoids subjectivism, so that we don't have to regard the states of particles as dependent on our knowledge in some sense, like we do under the Copenhagen interpretation. And the second major advantage is that we can understand the so because we're representing particles as singular regions of this wave, that we can also represent the joining together or the encroachment of one singular region on another, so that you could have two particles could merge, or one particle could split into two. And so this gives us a way of representing the phenomena of particles of subatomic particles splitting and so on. But yeah, this is something I don't know a lot about, but Simondon here seems to be suggesting that it would not be possible to study the nuclear scale under the standard interpretation of quantum theory. And that has certainly not turned out to be true. There's been a lot of study of the nuclear scale. That's one of the sort of core regions of research in physics over the last 50 years or so. And most physicists do accept the Copenhagen interpretation of quantum theory. So I guess Simondon is in a sense making a prediction about these research programs about whether they will be fruitful or not, and his prediction turned out not to be correct about the standard interpretation of quantum physics. So I guess an interesting question here is whether, so to what extent Simondon's conceptions are dependent on this double solution theory, and so if he was wrong about the idea that the standard interpretation of quantum physics would not be able to account for nuclear phenomena, is that like something that is that a flaw in his broader theory of individuation, or is this something that we can sort of regard as an isolated mistake or failed prediction or something like that? I'm not sure. My tendency would be to suggest that I think everything in Simondon's theory sort of hangs together pretty tightly. He's not like he's certainly a systematic thinker. He has a big picture in mind, and how the different pieces fit together at all times. So I think it would be hard to sort of cut out this one piece of his theory and say this piece was wrong and the rest is good. But I'm not super familiar with the secondary literature on Simondon actually, but from what I've seen, this area doesn't seem to be really addressed much. Like there isn't much secondary literature on his relationship with quantum physics and the double solution theory. There was that paper that we talked about a little bit last time, which talks about Simondon in relation with quantum physics, but it doesn't address the double solution theory and this issue of what the failure of the prediction regarding the research programs, what impact that has on the rest of Simondon's theory. I don't know if anyone's worked on that at all. Okay, so we can start the next subsection. I can read a bit. So subsection 3, the theory of the double solution in wave mechanics. However, it is important to note that if we begin by acknowledging that the physical individual should not be considered as a reality limited to itself and defined by its spatial limits, but rather as the singularity of a wave, i.e. as a reality that can be defined by the inherence to its properties, but which is also defined by the interaction that it has with other physical realities at a distance. The consequence of this initial breadth in the definition of the individual is that the notion remains affected by a coefficient of realism. Conversely, if we begin by upholding the opposite notion of the individual as being defined stricto sensu as a particle limited by its dimensions, then this physical being loses its reality, and probabilistic formalism replaces the realism of the preceding theory. It is specifically in probabilistic theories, which accept the classical notion of the individual from the start, that this notion is lacking due to the progress in the theory of the probability wave. According to Bohr's expression cited by Louis de Bruy, corpuscles become unsharply defined individuals within finite space-time limits. The wave also loses all realist physical signification. According to the expression of Détouche, it is nothing more than a representation of probability that depends on the knowledge acquired by the one who utilizes it. Quote, it is personal and subjective like the assessments of probability, and like them, it is abruptly modified when the user acquires new information. This is what Heisenberg has called the reduction of the packet of waves by measurement, a reduction that would alone suffice to demonstrate the non-physical characteristic of the psi wave, end quote. This probability does not result from an ignorance. It results from pure contingency, such as pure probability, which does not result from a definite hidden determinism that is calculable according to hidden parameters. Hidden parameters would not exist. The physical individual, the corpuscle, becomes in the theories of Bruy and Heisenberg a set of potentialities affected by probabilities. It is nothing more than a being that appears fleetingly, sometimes under one aspect and sometimes under another, in conformity with the notion of complementarity that belongs to Bohr's theory and according to the relations of Heisenberg's uncertainty principle, which are the foundation of an indeterministic and probabilistic theory. In general, neither a well-determined position, a speed, nor a trajectory can be attributed to the corpuscle. It can only be revealed as having a certain speed or position the moment when its measurement or observation is made. At each instant, so to speak, it possesses a whole series of possible positions or states of movement, since these various potentialities can be actualized at the moment of the measurement with certain probabilities. The associated psi wave is a representation of the set of the corpuscle's potentialities with their respective probabilities. The extension of the psi wave in space represents the indetermination of the corpuscle's positions, which can be revealed to be present in any point whatsoever of the region occupied by the wave with a probability proportionate to the square of the wave's amplitude in this point. The same applies for the states of movement. The psi wave has a spectral decomposition in a Fourier series or integral, and this decomposition represents all the possible states of a measurement of the quantity of movement, the possibility of each possible result of such a measurement that is given by the square of the corresponding coefficient of the Fourier decomposition. This theory has the fortune of finding in front of it, and ready to serve as its means of expression, a perfectly adequate mathematical expression, the theory of functions and proper values, developments in a series of proper functions, matrices and Hilbert space. Thus, all the resources of linear analysis are immediately usable. The double solution theory is not as well served by the current state of development of mathematical formalism. It seems that a certain irregularity in the development of mathematical thought, according to various paths, has led to a much greater facility of expression for the indeterministic and probabilistic theory than for the double solution theory. But the privilege thus given to a certain state of mathematical development to one of the interpretations of the wave corpuscle relation should not be considered an index of the superiority of the easily formulable doctrine in terms of what concerns the value of the representation that it gives of physical reality. It is necessary to dissociate formal perfection from fidelity to the real. This fidelity to the real is translated by a certain capacity of discovery and fruitfulness in research. However, the indeterministic and probabilistic theory of the relation between waves and corpuscles seems to have lost this power of discovery and is closed with an increasingly remarkable self-constructive formalism, S matrices, minimum length, non-localized fields, that nevertheless do not allow for the resolution, for example, of problems relative to the stability of the nucleus. So he's sort of going over again the opposition between the standard indeterministic and probabilistic theory, and on the one hand, and then the double solution theory on the other. And so he suggests that it's the state of mathematics that has led to the indeterministic approach being favored rather than the deterministic one. So the theory of linear analysis was available to the indeterministic theory, and so there were well understood mathematical constructions that could be used in the indeterministic theory, whereas the double solution theory didn't have the same mathematical resources available. So that's what Simondon suggests is behind the fact that physicists favor the indeterministic theory over the double solution one. And just a minor translation note here: when it says proper values, that should be eigenvalues. The term is a little bit different in I don't know exactly why, but in English we use the German term translation for this concept. So yeah, that's something missing in the translation. Okay, so I think we can go on. This will probably be our last page or so that we read. If someone else would like to read.
Louis de Bruy considers this opposition between the two conceptions of the wave-corpuscle relation as essentially residing in the deterministic or indeterministic postulate. We could also consider that what is in question is the representation of the physical individual, at first in an elementary sense, but then on all levels. Probabilistic theory can only be probabilistic because it considers that the physical individual is what seems relative to the measuring subject. There is something of a recurrence of probabilities installed in the very being of the physical individual, despite the contingency of the relation through which the event of measure intervenes. On the contrary, at the basis of the double solution theory, there is the idea that relation has the value of being and really belongs to being. A particular wave belongs to the individual, and this individual is its center and singularity. The individual is what contains the instrument through which relation is established, since this relation is that of a measurement or some other event that conveys an energy exchange. Relation has the value of being. It is an individuating operation. In the indeterministic and probabilistic theory, a certain static substantialism of the physical individual remains in the subject. The individual can indeed be one of the terms of the relation, but the relation is independent of the terms. In the end, we could say that relation is nothing. It is only a probability for the relation to occur here or there. Relation is not of the same nature as the terms. It is a purely formal thing, something artificial in the profound sense of the term, when there is a measurement, i.e., a relation of subject and object. This formalism and this artificiality, which come from an overly narrow definition of physical individuation, then reflects back onto the usual definition of the individual, which is practically defined only by the relation. It then becomes this, quote, unsharply defined individual, unquote. Yet the individual precisely cannot be, quote, sharply defined, unquote, at the start, before any relation, because it carries its possibility of relation around it, and is this possibility of relation. Individuation and relation are inseparable. The capacity of relation belongs to the being and enters into its definition and into the determination of its limits. There is no limit between the individual and its activity of relation. Relation is contemporaneous with being. It belongs to being energetically and spatially. Relation and being simultaneously exist as a field, and the potential that relation defines is veritable, not formal. Just because an energy is in a potential form doesn't mean that it does not exist. The response will be that we cannot define the potential outside of a system. This is true, but it is possible that we need to postulate that the individual is a being which cannot exist as an individual except in relation with a non-individuated real. In the probabilistic conception, it is postulated that the individual can exist alone and afterwards is found to be incapable of incorporating relation, which seems accidental and undetermined. Relation should neither be conceived as immanent to the being nor as external and accidental to it. These two theories unite in their mutual opposition in the sense that they suppose that the individual could be alone by right. If, on the contrary, we posit that the individual forms part of at least one system, relation becomes as real as the individual qua being, which could abstractly be conceived as isolated. The individual is being and relation. It is a center of activity, but this activity is transductive. It is exerted across and through a field of forces that modifies the whole system in terms of the individual, and the individual in terms of the whole system. Relation always exists as potential, but it may or may not at a certain moment in the process of correlatively modifying the individual and system. Quantum laws seem to indicate that this relation only operates step by step and not continuously, something that guarantees stable states for both the system and the individual despite the conservation of potentials. I guess I'll just finish this paragraph. Formalism supposes that the individual is conceived before relation, which then remains purely calculable without being subjected to the conditions of the individual's energetic states. The individual state and its state changes are not conceived as the principle and origin of relation. In formalism, relation is not conflated with its energetic modality. On the contrary, in realism, relation is always an energetic exchange that implies an operation on the part of the individual. The structure and operation of the individual are tied together. Every relation modifies the structure, and every change of structure modifies the relation, or rather is relation. For every change of the individual's structure modifies its energetic level and consequently implies an energy exchange with other individuals, constituting the system in which the individual has received its genesis.
So here he ties this discussion of quantum physics back into the notion of the individual and the essential relativity of the individual, in the sense that an individuated being is always part of a system with something that is non-individuated, something that remains pre-individuated. And so this potential energy in the system is this unindividuated term that the physical individual is always related to. So in the case of the particle, we have the singular region and the wave that surrounds it, and the individuated region, or the individual aspect is always relative to a pre-individual aspect, and so because of that, we can understand the relation between them as a physical relation and not a strictly formal relation. And so he argues here that the probabilistic interpretation of quantum physics presupposes a substantialist, or the classic notion of the individual as something self-contained, and then sort of secondarily tries to understand the relation between that individual and the observer, and then gets into the difficulties of having to understand that relation as being sort of indeterministic, and having an inherent indeterminacy, so that it's not the position and momentum of a particle are not determined until they're measured, and the understanding of understanding the particle as a physical individual, always in relation to something non-individuated, allows us to understand that relation as a physical relation, rather than a purely formal one. And so that's what Simoneau thinks we can derive from the double solution theory, is an understanding of how we can grasp individuation as a real physical individuation of these physical entities, rather than something purely formal. Okay, so we're almost at time, so I think this would be a good place for us to stop for today. unless anyone has any final comments they wanted to make.
I just want to say that there's a light at the end of the tunnel, because I think maybe next session we'll finish this physical individuation, quantum physics stuff.
Yeah, so thank you for your persistence, everyone, in pushing through the difficult stuff. It won't be long before we get to something at least a little bit more concrete that we can at least picture what's going on in a way that we can't in this section.
But I think I also had a difficulty in understanding, but at the same time, this part is definitely like Simondong theory's singularity. Like, it's like, yeah, once I read it again, if I can understand much more, then it will be fantastic. And then your explanation definitely has been really, really helpful. Thank you.
Well, you're very welcome. And thank you, everyone, for your questions and comments. So I'll see you all next week, and we'll pick up from page 153.